Hello everyone, welcome to the week 9th of this course Diffusion in Solids. So in the last week we started talking about the diffusion measurements using the nuclear methods. We talked about the direct measurements and the indirect measurements as well. Now, we will continue a little bit more about nuclear methods today, under which we will be covering what is known as Mossfire spectroscopy and quasi-electric elastic neutron scattering. So, these are some of the keywords. So, the Mossfire effect was detected by the Nobel laureate in physics, Rudolf Mossfire. It was detected in 1958, for which he received the Nobel Prize 3 years later. What is this effect? It is the recoil-free emission and absorption of gamma radiation by atomic nuclei. Now, we are not going into too much detail of how exactly this happened, but you can, for your own interest, try and find out more about this. But in a brief, it is more like whenever an atomic nuclei is emitting gamma rays, then there will be a recoil that it will experience. But when the emission or the absorption happens without this recoil, that is known as the Mossfire effect. Okay, recoil is more common. For example, you can observe it in your daily lives as well. You play with this toy guns which throws out ball, a little bit of backward push one feels. Similarly, anything if it ejects anything, something ball or something like that, then you will feel a backward push. So, that recoil is quite common. But when the emission and absorption is recoil free of this gamma radiation, that is known as the Mossfire effect. So, but as you can understand, as I said, that it is not that common. So, it can be used to deduce information about the movement of atoms, for which there are few Mossfire isotopes like iron 57, which is one of the most important isotopes that is used in Mossfire spectroscopy, then tin and some couple of others. So, it uses basically two samples, one which plays the role of the source and another which plays the role of the absorber of the gamma radiation. So, the source nuclei emit gamma rays, and some of which are absorbed by the absorber without any atomic recoil. So, that is what constitutes the Mossfire effect. So, this is the source where it is typically a moving source experiment, and then you have an absorber, then you have a detector in place. I will explain a little bit more about this in the coming slide. So, this radio isotope 57 CO, this is what is frequently used as the source. Okay, so it decays with a half-life time of 271 days into an excited state of the Mossfire isotope 57 Fe, which has a lifetime of 98 nanoseconds. So, this tau n refers to the lifetime at this excited energy level, which is the 98 nanoseconds. So, in the previous figure, what we saw, the source contains this isotope frequently 57 CO, which when it decays, it goes to the excited level of iron 57. And this decay of iron 57 after this lifetime of 98 nanoseconds happens with the emission of a gamma radiation, which equals the energy of which equals around 14.4 kilo electron volt, and then it comes to the ground state of 57 Fe. 57 Fe is a stable isotope with around 2.2% natural abundance. Now, if you can incorporate this Mossfire isotope in a crystal, then the recoil energy of this decay is actually transferred to the whole crystal. So, it is not just to that atomic nuclei, it is to the whole crystal, and then the width of the emitted gamma line becomes extremely narrow. Now, if the fraction of this emitted gamma rays is absorbed without recoil in the absorber, which also contains the mass pair isotope. So, we saw here that you have this source which basically converts to the 57 iron, and this 57 iron once it decays by emitting gamma rays, then these gamma rays are also absorbed by the absorber, which also contains the mass pair isotope. Now, in the experiment, usually the source is moved relative to the absorber with the velocity v. Then this Doppler shift of the source radiation, you all know that there is a Doppler effect coming whenever you have a moving source. So, then this delta E is equal to nu by C into E of gamma. So, line width in the absorber is then recorded. So, the detector records the line width as a function of the relative velocity or as a function of the Doppler shift delta E. So, the line width is usually what is recorded. Now, how it is related to the diffusion. So, remember, so if what we are talking about is this width, okay. So, this gamma naught that you see, this is the capital gamma. So, this gamma naught you see is the initial line width, okay, which is quite narrow when let us say no diffusion is happening, and that what is the origin of this line width is what is explained here. Now, when the diffusion in solids is rapid, okay, remember when the diffusion in solids is rapid, it leads to the broadening of Moss pair spectrum. Okay, if you remember one figure I showed you when we started about the techniques that gives you the range of diffusivities each technique can measure. So, if you will go back to that figure, you will see that typically MBS we can measure the higher range of diffusion coefficients. So, if the diffusion in solids is rapid enough, then it leads to Moss pair spectrum broadening. So, why broadening happens? So, at low temperatures, suppose if you are at lower temperatures, then this Moss pair nuclei will stay on the lattice during the emission. So, during the emission, they will stay on a particular lattice site. So, if at low temperatures there is no diffusion, whatever is the natural line width gamma naught is observed. Okay. So, there is an emission happening, there is an absorption happening. So, during the emission the nuclei is stable or it stays on its lattice position because the diffusion is very minimal. So, that product tau naught into tau n where tau n is the lifetime of the excited MB level, if it is greater than equal to h bar. Okay. So, this is usually comes from the Heisenberg's uncertainty principle. So, sorry, not so there is a small correction, this is gamma naught into tau n should be greater than or equal to h bar. So, this comes from the Heisenberg's uncertainty principle. So, that means if the gamma naught is actually dependent upon the tau n. So, at low temperatures when the diffusion is very low, the nuclei stays on the lattice during the emission. Now, what happens at high temperatures? At high temperatures the diffusion is enhanced. Enhanced diffusion, what it does is the atom resides on one lattice site for a time tau bar between two successive jumps. Now, if tau bar is similar or less than tau n, then the MB atom changes its position during the emission. So, let us understand this carefully. This tau bar is the time between the two jumps. That means, suppose if it is here and here, between the two jumps the time is tau bar, and the lifetime of the excited MB level, that is tau n. So, if this tau bar is less than tau n, that means by the time the decay happens, the atom would have changed its lattice site. So, that is what is observed for the higher temperatures when the diffusion is rapid enough. So, that means that the one wave packet now splits into several short packets. Okay. So, this emission is happening, and during the emission before it can go down to the lower, before it can emit and go down to the ground state, the position or the lattice site of the nuclei has changed. So now in essence what is happening is that one wave packet, you can say it splits into several short packets. This causes a broadening of the line width. So this is represented here, that by the time it moves the position, it is now emitting several short packets of photons. So this leads to an additional broadening of the line width, which is given by delta gamma is equal to gamma minus gamma naught. And this, if the tau bar is sufficiently smaller than tau n, then delta gamma is almost equal to h bar by gamma bar. Delta gamma is approximately equal to h bar by tau bar. So if we neglect the correlation effects, then this broadening, the delta gamma, can be related to the diffusion coefficient by this relation, d is equal to d square by 12 into delta gamma by h bar. So this d is the jump length on the Bravais lattice, and this delta gamma is the broadening of this width of the peak. So you can see that if we can measure this broadening, we can calculate the diffusion coefficient. So people try to do more quantitative and more rigorous analysis to understand or to quantify the spectrum. I will just show you some equations to let you get a feel of the equations involved. But I don't say that you have to memorize it, but please understand few terms in this. So for example, I'm not going to ask you in your exam to write the equation, okay, but understanding of it is more important. So this absorption spectrum is quantified by a parameter sigma, which is dependent on q and omega, which is this integral. This integral involves a function known as the self-correlation function, which is written as gs, which is a function in space and time. So this q is basically a wave vector, and r is basically the jump vector. See this and here the gamma naught is the natural line width of the MB transition. It should be okay to understand that when we have a function of r and t, it's because you are in space and time, and here q and omega comes into a picture, because ultimately what we are saying is that the time between the emission and the changing of the lattice site. So it's the time and space really we are dealing with. Now this self-correlation function has two parts to it. One which is due to the lattice vibration, and this lattice vibration governs the intensity of the resonantly absorbed radiations. So the radiations which are absorbed, and another part is the diffusional motion which decides the shape of the mass pair spectrum. So this lattice vibration ultimately leads to or are quantified by known as quantity, a parameter known as Debye wall factor, which is represented as FDW. So as I told you in the previous picture here, that there are these several packets of waves which are emitted. So remember again let me point out that if the temperature was low enough and if there was no diffusion happening, this nuclei would have stayed here, and there will be one you can say along larger packets of waves emitted. Now it is cut into several short packets, because the atom is moving from one place to another, or the nuclei is moving from one lattice site to another within that time. So the interference now between these packets depends upon the orientation between the jump vector r of the atom and the wave vector q. So again, if we go back to this figure, you can see that there are two quantities. What is the vector of this wave? So, at what angles the waves are coming out, and what is the jump direction? So, what is the jump vector? So, the orientation of these two will decide the interference between this wave packets. So, when we want to relate it to diffusion for random jumps on a Bravais lattice, this shape of the resulting MBS is a Lorentzian. So, the sigma is a Lorentzian type of function which is proportional to FdW delta gamma, which is a function of q by 2 divided by delta gamma by 2 whole square plus h bar omega whole square. And this delta gamma is full peak width at half maximum. So, this delta gamma is further written as 2h bar by tau bar multiplied by 1 minus sigma wj into ij, where wj into ej is equal to this relation, which basically describes the orientation between the q and r. And Wj is also called as the probability for a displacement to a coordination shell J, and this Ej is the corresponding structure factor. So, you can say that's the structural terms that are coming here. Nj is the number of sites in the coordination shell J, and Rk is the displacement vector to the sites in the shell J. So, if the diffusion is mediated by vacancies, then these terms get slightly modified to WENC. You see the subscript here, and you see another subscript which is ZENC. What is WENC? Is the probability for a displacement of Rj by an encounter with a defect. Okay, so that means whenever we have seen this, that whenever the defect comes into picture, there is a specific probability comes here. So, this is the probability for a displacement of Rj by an encounter with a defect. Then Z encounter is nothing but the average number of jumps performed by a MB atom in one encounter. So, one encounter is basically the one exchange between the tracer and the vacancy, and after this, after the first jump, how many jumps once the tracer has to make again to come back to the same vacancy. So, this is known as complete one encounter. Now, both sigma and the delta gamma depend upon the relative orientation between q and r. So, you can see here that q and r comes here also, and previously we saw that sigma also contains q and r terms. So, that means if you have a single crystal orientation, the information about the length and the direction of the jump vector is obtained. So, in principle, because here both the delta gamma and the sigma are dependent on q and r, in principle, if you have a single crystal, then by changing the orientations, which is possible sometimes, you can get information about the length and direction of the jump vectors, which is not usually possible in many techniques. So, this is an example here which shows the broadening of mass by a spectrum due to diffusion. Here you can see this is for the iron palladium multilayer, and it can be seen that with the increasing the retention time, the diffusion profile gets more and more flattened, which indicates the intermixing of the adjacent isotope layers. So, you can refer to this paper to get more details about this. So, the key advantages of the mass wire spectroscopy is sensitive. It is sensitive to elementary steps of diffusion on macroscopic scale. Then it allows the direct determination of jump vectors, and the jump rates is possible for the single crystals, and you can use for the deduction of the diffusion coefficient, of course. The limitations are that it is usually only possible at higher temperatures, so that this tau bar is comparable to tau n. The nuclei studied must have a large value of the recoilless fraction, otherwise you cannot have the sufficient intensity. Then only limited number of isotopes are suitable for such mass pair effect. I already listed out this previously. Then the diffusional line broadening should be comparable on or larger than the natural line width of the MB transition. So that means whatever is the natural line width, if your broadening due to diffusion is not sufficiently large, then you cannot detect it. And therefore, only large diffusion coefficients in the range of 10 power minus 14 to 10 power minus 10 meter square per second, for example, for iron 57 can be measured. So, this was about the mass pair spectroscopy. Let us move to the next technique, which basically deals with the scattering of neutrons. The technique itself is the quasi-electron neutron scattering technique to basically understand or measure the diffusion coefficients. So, coming to the neutrons, the scattering of beams of slow neutrons which are obtained from the nuclear reactors or other high intensity neutron sources, it can be used to study structural and the dynamic properties of the condensed matter. The unique thing about the neutrons is, if you see this graph schematic for the frequency and the lambda for different types of EM waves, what you will see is for EM waves, we know that nu is equal to c by lambda. For neutrons, nu will be equal to h by 2m into lambda square, where m is the mass of the neutron. Now, the atomic frequencies usually are equal to the infrared or the microwave frequencies of the electromagnetic waves. The R atomic here refers to the atomic interatomic distances, which are equivalent to the wavelength of the X-rays. Now, lambda and nu for the slow and the thermal neutrons are equivalent to both R atomic and the nu atomic. So, that is why the use of neutrons allows us to probe the structural and some of the dynamical properties of the condensed matter. And we know that they are uncharged, they have weak interaction with matter, so therefore it is easier to probe bulk property. It is possible to use wide temperature range and also apply magnetic fields in combination with them to probe various properties. So, the neutron scattering, basically during the neutron scattering, there is a energy transfer which is given by h bar omega, it is equal to E1 minus E naught, where E1 and E naught are neutron energies after and before the scattering. The momentum transfer h bar q is equal to, so the scattering vector q is equal to k1 minus k naught. Again, k1 and k naught are the neutron wave vectors after the scattering and before the scattering. So, this is how there is a neutron wave coming with a wave vector k naught and the energy E naught, and then it is scattered and the wave vector now changes to k1 and the energy changes to E1. So, this is the angle at which it is scattered. So, this is typically the relation between k1, k naught and q. Schematically, using the vector diagram, you can represent it. So, the lambda, the wavelength is equal to 2 pi by k1 and the lambda naught is equal to 2 pi by k naught. Q is equal to 4 pi by lambda naught sine theta by 2, and this theta is what is known as the scattering angle. So, typically the Q is in the range of 1 to 50 nanometer inverse. Now, when there are inelastic peaks come, so this is about the elastic. When the inelastic peaks come, they comes due to the absorption and the emission of phonons. So this we also show here schematically. So this at the center, what you see is the elastic peak where the energy transfer happens, and inelastic peaks where the absorption and emission of the phonons happens. So there the scattered intensity also you can see the peak here. Now, what happens in the quasi-electron, quasi-elastic neutron scattering? So, basically, let me just show you. So, the major features are, so when you have the perfectly elastic neutron, perfectly elastic scattering at certain value of h bar omega, which is h bar omega is 0. So, you get a perfectly sharp peak, which is also known as the Bragg peak or the elastic peak. Now, due to the diffusional motion, this peak can be a little broad, and that is what is known as the quasi-elastic peak. And the broadening of this, the delta gamma, is related to diffusion coefficient as 2d into q square. So, delta gamma is the full width at the half maximum of the Lorentzian shaped quasi-elastic line, and d is the self-diffusion coefficient. And this, as I said, the broadening is due to the diffusive motions. If it is the particles are at rest, then in principle the delta gamma is equal to 0. So, there at sharp line is observed. So, this elastic line, it originates when the neutron transmits the momentum to the sample without any energy transfer. Okay. So, that means if you understand from the previous picture, so here if the energy coming is also E0, so then only the momentum is changed, the energy is not changed, that is a perfectly elastic scattering. Okay. So, that is the case where you get the sharp peak. But if there is a diffusional motion involved, then there is a broadening which occurs in the quasi-elastic peak in this peak, and this is known as now the quasi-elastic peak, and the broadening of this is related to the self-diffusion coefficient. So, this is one thing that I hope you have tried to find out common. Let us say we talked about certain techniques in the last lecture also in the nuclear methods, and now we talked about MBS, and we are talking about the QENS. So, here the effect of the atomic motion on the certain signals or certain peaks leads to the broadening, and that broadening, if we can measure, if we can quantify, that can give us the information about the diffusion coefficient. Now, in the various techniques, what is broadened or what particular signal we are studying, that is different depending on the technique that we are using. Okay. So, moving ahead, the intensity that you get in these neutron scattering experiment is governed by what is known as the dynamic structure factor, which is delta IS is equal to I naught into N into V d square sigma by d sigma d omega multiplied by delta omega into delta. So, omega, both are omega, one is capital omega, one is small omega. So, V is the sample volume, delta sigma is the solid angle. Now, d square sigma by d omegas is equal to k1 by k naught into sigma by 4 pi into s, which is a function of q and omega. So, here sigma is called as the cross section for a rigidly bound nucleus, and this sigma is equal to 4 pi b square, where b is the scattering length of the nucleus. And this S is the dynamical structure factor, which depends upon the scattering vector and on the energy transfer. But this structure factor is independent of the interaction between the neutron and the nuclei. So, it is basically related to how much the energy is transfer and how much is the scattering vector. This term d square sigma by d omega, capital Omega, d small omega, it contains two parts. One is the coherent scattering, another is the incoherent scattering. And this coherent scattering, that's coherent scattering occurs due to the average scattering from the different isotopes. Okay, so if you have different isotopes in your sample, then average scattering from the different isotopes leads to the coherent scattering, which is given by 4 pi b square. This b bar square, this b bar is nothing but the scattering by each nuclei. So, Ci is the fraction of different types of nuclei. So, b bar is summation of Ci into Bi. Now, due to interference of partial neutron waves originating at the positions of different nuclei, this is what leads to the coherent scattering. And this coherent scattering is basically proportional to the Fourier transform of the correlation function for any nuclei. And this coherent scattering also leads to the interference effects, and collective properties can be measured, for example, the Bragg diffraction peaks. So, the coherent scattering part basically it leads to the interference effects. If you will see, we will see later that for the diffusional broadening, it is actually the incoherent scattering which is plays a more important role. Whereas the coherent scattering, where collective properties can be studied, one classic example is the diffraction peaks are generated due to the coherent scatterings. The incoherent scattering, it is proportional to the deviation of the individual scattering lengths from the mean value. So, this incoherent scattering is equal to 4 pi b square minus b bar square, with b bar square is equal to summation Ci into Bi square. And this b is basically the individual scattering length, b bar is the average, and this incoherent scattering factor is proportional to the Fourier transform of the correlation function of the individual nuclei. Now, this incoherent scattering is connected to the isotopic disorder and to the nuclear spin disorder. So, only a mono isotopic ensemble with the spin I is equal to 0 would scatter in a totally coherent manner. That means, you will always have if you have a completely one type of isotope only, where the spin also is I equal to 0, then only you can get the scattering in totally coherent manner. Otherwise, there will be always some incoherent scattering that will take place. So, this is the thing that this now this incoherent scattering leads to a peak like this, which is related to the diffusion coefficient. I will give you the expression shortly in the coming slide. So, this incoherent scattering, like we saw for the MBS, is related to the self correlation function G and exponential Q R minus omega t, which again talks about the wave vector and the jump factor. And this self correlation function follows a Gaussian behavior, which is equal to 1 by 4 pi dt 3 by power 3 by 2 exponential minus r square by 4 dt. So, this d comes into picture here. So, d is the self diffusion coefficient of atoms. So, if you take a series of Fourier transforms of this g, first in space, then in time, then finally you can write the incoherent scattering function for a random jump motion on a Bravais lattice is 2 by pi delta gamma divided by delta gamma square plus omega square. So, this is the incoherent scattering function, and this again this delta gamma is equal to 2 by tau bar 1 minus sin q d by q d, where the tau bar is the mean residence time for an atom on the lattice side. So, this d is equal to the length of the jump vector. So you can see here that if if you are at very low temperatures where the diffusion is very slow, that means you can say that the tau bar is very, very high. So let's say in an extreme case where the diffusion is totally 0, tau bar is infinite, and therefore this delta gamma will also come to 0. So this delta gamma comes into picture because of the diffusion of the atoms or the atomic jumps. If we write this expression for a simple cubic Bravais lattice, then we can write like 2 by 3 tau bar, 3 minus cos qx d minus cos qy d minus cos qz d, where qx, qy and qz are xyz components of q. For the vacancy mediated diffusion, this can be the expression can be written in terms of the encounter W encounter and the cos q into Rm, where W encounter is the probability that during an encounter an atom originally at Rm equal to 0 has been displaced to lattice site Rm by one or several jumps. So, what are the examples where this QENS is used? Primarily for sodium self diffusion in ion conducting rotor phases, sodium self diffusion in sodium single crystals, hydrogen diffusion in palladium. Remember again that this QENS, I will show you in the next slide also, to measure the broadening on a sufficient scale, you need the diffusion to be very fast. That's why it is usually for the phases where the diffusion can occur fast, or where if you can employ the higher temperatures. So the advantages include that, again, like MBS, it allows the investigation of elementary steps of diffusion in solids on a scale of atomic dimensions and times. And the hydrogen, sodium, vanadium diffusion measurements are possible. For these, MB isotopes are not available. So that way the QENS can give you some unique determinations. The limitations, like MBS, it requires high temperatures so that the tau bar is short enough to produce a diffusional broadening, which exceeds the energy resolution of the neutron spectrometer. For the time of flight spectrometry, the resolution is in the range of microelectron volt to 0.1 millielectron volt, and as a result, only high diffusion coefficient somewhere in the range of 10 power minus 12 to 10 power minus 8 meters square per second can be measured. And again, like this, like MBS, it is only possible to measure for few elements. So with this, we will close talking about the nuclear methods, as well as this ends our discussion on diffusion measurement techniques. From the next lecture onwards, we will see different parts of diffusion which are important other than the lattice. Thank you.